Those Space People, a podcast series of casual cosmic conversations with people working on exciting space projects. Welcome to Thermal Lens, a special series focusing on thermal remote sensing, created by me, your host Rachana Mamidi, Agnieszka Sojinska, and Jennifer Susan Adams. Agnieszka is currently a research associate at the University of Leicester in the UK and has been working in the area of thermal remote sensing since 2017. Jennifer is a postdoctoral researcher at the University of Zurich in Switzerland and is currently focusing on measuring land surface temperature over forests. Agnieszka and Jennifer are also chairpersons of the Thermal Remote Sensing Special Interest Group of EARCEL, the European Association of Remote Sensing Laboratories. This group aims to bring together all the relevant stakeholders and provides a communication platform in the form of workshops, special sessions, seminars, and more. Agnieszka and I are back again, and we are recording today's episode with Ellis Freedman. Ellis is the founder of Serious Science, a US-based consulting company providing design and analysis support for satellite imaging systems. He has 40 plus years of experience in radiometry for infrared as well as visible to shortwave infrared imaging across multiple remote sensing missions, ranging from government systems to commercial systems, including NASA's Landsat program. As a systems engineer with many degrees in physics, Ellis was involved in all mission aspects throughout his career. He has also served as a visiting lecturer on remote sensing payload design and IR phenomenology at Villanova University in the USA. Our conversation with Ellis covered a lot of interesting topics and lasted for more than an hour. So, to make it easier to follow, we've divided it into two distinct episodes, each centered around a specific theme. So let's kick off with the first segment that contrasts large space agency missions with smaller new space missions. And welcome to the podcast, Ellis.
Thank you very much.
So, Ellis, you're currently a consultant for a bunch of remote sensing companies through your own company called Serious Science. And previously, you have contributed to the Landsat missions during your time at Lockheed Martin. So, what exactly was your role in these missions, in the Landsat mission and other large missions that you've contributed to?
Well, originally, my biggest project was to develop and test the radiometric calibration and image processing of high resolution infrared systems. And eventually, after at least a couple of decades at that, I was brought into the Landsat 7 program as part of the Systems Integration Group. And my role was to lead the development of the radiometric calibration and processing of the VSWIR and the long wave infrared payloads, as well as something called the Hermsy payload. Just as a little background, originally Landsat was supposed to carry two payloads, two cameras. One was what eventually became the Enhanced Thematic Mapper Plus, and the other was called Hermsy, the High Resolution Multispectral Imager. That was actually a payload from the US Air Force. My team was responsible for defining a lot of the requirements for Landsat that are still used today. Unfortunately, when the Air Force pulled their support from Hermsy, from the program, they took the payload off of the satellite. The systems integration and ground processing contracts were eliminated. But even so, many of the requirements I wrote, many of the analyses were included in Landsat. And I was also on the proposal teams from Lockheed Martin for all subsequent Landsat missions.
What exactly led you to begin to start your company, Serious Science? Was it like a very obvious transition to start consulting for usually someone in your position with your experience, or was there anything that really triggered you to start this consulting company?
No, it wasn't obvious at all. In fact, for quite a while, I couldn't find anyone who was interested in hiring me as a consultant. No, I left Lockheed Martin uh, because, frankly, I grew tired of the large mission bureaucracy, and I left in the hopes of providing engineering support to smaller, more practical and rapid remote sensing systems. Some of the programs that I worked on between the time that we started and the time of launch was sometimes as long as 10 to 15 years. And it's really hard to get any satisfaction out of something when you only see perhaps 2 launches in your lifetime.
This is very interesting because this brings us exactly to the subject of our conversation, that is the differences between the large agency missions and the smaller commercial missions. What you just said rapid. So here we have our first difference in the timing. And so to keep it a bit structured, can you say something on like how is such a large agency mission initiated? What drives it? What is the main focus point in the planning phase? And for instance, can you extrapolate from your experience in the Landsat missions?
I can try. Um, and I'll preface this by saying that uh, the focus points in the planning phase that I'm going to talk about are what should be done for successful missions, not necessarily what is always done for these missions. The missions always begin with a clear definition of the user needs and objectives. And surprisingly, that doesn't happen very often. Um, but along with that, typically we have to do what are called utility studies, and they're carried out to discover or confirm the value of certain parameters for the users. After that, there's often a request for information, an RFI that goes out, that's published to gather information on what people think are the viability of the mission concept and any new ideas that industry may have or government for for modifications to the mission. And from there, the requirements must be defined for the mission, for the users, and the various segments as you flow down the requirements, such as for the satellite bus, the payload, and the processing. That's really how you have to begin. Very often, as I said, this doesn't necessarily happen. This is the way I was taught originally, and we were very successful. And at some point, at least in my case, the US government decided to abandon that process, and it became disastrous. So that's why I wanted to say that this is specifically for successful missions.
This still kind of stays in a way because missions currently, for instance, like surface biology and geology in NASA, are strongly basing on this decadal survey, basing on needs and requirements by the people.
Yes, but each mission is a little bit different. To be honest, I'm not familiar with that particular mission. I know about it. I'm just not intimately familiar with how it was started. Um, Part of the problem with these planning phases is there are certain challenges that come up. One of the biggest ones is that users do not understand the engineering implications and the limitations that come with meeting their objectives. Users, at least in organizations like NASA, tend to be scientists. There's nothing wrong with that, but a scientist is not an engineer, and they may not understand some of the limitations that occur. Uh, and users often have a difficult time distinguishing between what they need to accomplish the mission and what they want. I've been on different projects where, for example, they may only need, for example, 1 degree accuracy in temperature estimation. But then they will say, well, but can we get a tenth of a degree? Well, maybe it would cost you an awful lot of money. It wouldn't get you much more, but they tend not to understand the limitations. And then flowing requirements down to operations and payload and processing, that requires careful negotiations with the various contractors. And contractors can be territorial, and they're often guided by their management profit considerations. So they're going to try to get as much as they can for as little as they can. And that sometimes leads to conflict. Now, on top of it all, for large missions, inevitably there's a bureaucracy. The bigger the mission, the bigger the bureaucracy. And for each additional person in the bureaucracy, you end up with someone who wants to disagree with something along the way. Um, I, I hate to use a crude analogy, but I was once taught that every additional person in a bureaucracy acts like a dog. They want to spray whatever they're looking at and make it smell a little bit like themselves. And that's basically what happens in a bureaucracy. You end up with a lot of people trying to change things just so it smells a little bit like them. Um, and then finally, there's requirements creep. I don't know if you're familiar with the term, but uh, that's where you start out with initial requirements and you start your design. And as time goes on, the users will come back and say, well, can you give me a little bit more of this? Well, we hadn't thought about this before, but can you add that? And these have big implications where things have to go back to the drawing board, change the designs, change the manufacturing, all new analyses have to be done. And unfortunately, that's not just limited to large missions. That can occur in small missions as well.
Let's just come a little bit back and think and say, who are the target users of the large agency missions? Who does the agency try to serve in planning of such a mission?
Well, there are several, and it can be broken down in different ways. Um, for example, there are users that want to evaluate crop health and requirements. There are others that want to evaluate urban heat islands, for example, um, or power usage in buildings. Some are interested in subsurface effects, such as underground steam pipes can be seen in the thermal, even when you can't see them in the visible domain. And in the future, if they haven't done it already, hyperspectral thermal will be used for evaluating man-made gas emissions. Uh, Currently, they already use hyperspectral thermal for atmospheric sounders to determine atmospheric contents, things like ozone, water vapor, things like that. But in the future, as I said, if not now, because I'm not necessarily plugged into everything, um, hyperspectral can be used for detecting other types of gases that are man-made, which would be of great value to military users, to climate change people, to any number of organizations out there.
And if we wanted to categorize those users into, say, their employment, would you say they're more commercial users or science users or educational, administration maybe?
If you're talking about the large missions are generally government missions in some form or another. And government can be military, it can be, in the case of the United States, NASA, NOAA, National Weather Service, uh, any number of scientific organizations. Um, for smaller commercial missions, and I'm not including, I know that there are some missions that are fairly large from, say, Maxar, um, but I'm excluding those because those are actually really trying to sell to the government directly. Um, the smaller missions are are trying to sell to commercial areas, and those commercial systems can be doing any number of things. There's a big difference between the users of large systems and the small systems. Large systems are for users who want to push the limits of data quality and accuracy, and sometimes in anticipation of what may be needed for the advancement of science. Small systems tend to know what their minimum product quality necessary is to support commercial users and no more because they can't afford to overachieve because that goes against their business plan and it costs too much money. Does that answer your question?
Yes, absolutely. And this also dives already into the differences. We spoke already about the timing and the target users. And then how about initiation of such a mission? Do you think that the commercial small missions are rather initiated by enthusiasm, a market niche, or really some kind of a need that is driven from the community?
Or investor money.
Or investor money, yes.
Yeah, it can be both need and enthusiasm, or it can be neither. Um, Neither makes the system commercially viable, at least alone. What's required is not just both, but a firm understanding of the science and engineering involved and a good business model. That's the one big difference between smaller commercial systems and large government missions. And that's they have to make money at some point. The problem becomes one of making money, being profitable. 90% of small businesses fail very quickly. And small satellite missions are really no different. In fact, the last time that I checked, Planet, which is fairly large but has several small satellites, is still not profitable. They're not expected to be profitable for another 2 to 3 years, which means they will have gone for perhaps a decade losing money. Um, we may be experiencing something similar to the dot com bubble of the late 1990s. Um, we have a tremendous number of commercial small systems out there, and I'm sure that not every one of them will be successful. We currently have, the last time I checked, more than 7,000 active satellites in orbit. That's a lot of satellites to go around for what may not be um, enough users. So that would drive the price down, which makes it less profitable, and so on. So you end up with an endless cycle. So that's why I say it's not just need or enthusiasm. Yes, you may find some companies where someone is very enthusiastic about an idea that they have, or they may actually see a need for something, but that doesn't mean that it's profitable by the time that they're through.
These 7,000 satellites are also good business for space traffic management companies, right?
Yes, I've seen several companies try to get into that particular business, and it becomes very difficult. I think that I saw an article a couple of weeks ago in which I believe it was the space station had to move out of the way of satellites. There's just so much out there that they're getting in each other's way. And of course, I'm sure everyone is aware that if they collide, they create tremendous debris that end up hitting other satellites, and you end up with a cascade effect, which no one wants.
Absolutely. And then, if we think about the initiation of the mission, we spoke to Mike Abrams, science lead of Aster mission, about the NASA's way of initiating missions. He said that there are tests, that often sensors are being built as airborne precursors to the spaceborne sensor. I imagine that is not the way in the commercial smaller missions, is it?
Typically not. Typically, for smaller missions, there are already uh, airborne platforms out there, commercial ones, that have already collected a tremendous amount of data. And that's where some of the enthusiasm comes from, frankly. Um, it's usually too expensive to try to prototype for an aircraft mission to test things out and then build it for a satellite. They usually rely upon well characterized sensors that are already available off the shelf.
Now that you mentioned off the shelf, right? So commercial missions, especially small commercial missions, are using a lot of COTS, commercially off the shelf products, and it's also going towards a lot of miniaturization, right? So now, given this miniaturization, that means automatically everything inside the spacecraft is spatially closer. In turn, does this make the onboard thermal management difficult? Because that is one of the biggest challenges of thermal imaging payloads, right?
If you're asking, does the fact that you have heat emitting electronics closer to the actual telescope that you're using, if you're asking if that influences things, yes. Um, each design is different. I am working on a mission currently that has that problem. I won't say what mission, but yes, it can become a real issue. And again, that means you have to very carefully track the temperatures. Otherwise, you could end up with significant errors.
Apart from this, are there any other challenges that smaller missions have in comparison to larger thermal missions?
It's difficult to say. As I said, the problem is they're trying to save money to make it a viable business case. But at the same time, there are both engineering and scientific challenges. In order to actually design these systems, you have to do careful characterization and measurements, both pre-launch and post-launch. And often commercial sensors don't have the funding to carry out complete characterization in the laboratory. Usually after launch, it's easier, but pre-launch, it can become a problem. The main differences, I'd say, between large and small is that large missions seem to concentrate on data quality and precision because they're really science missions. Small systems usually uh, plan for full satellite constellations, so a lot of small sats versus one big satellite. And they concentrate on just enough quality to meet the mission requirements and gather as much data as possible. So, in that sense, uh, small systems have different challenges than large systems.
Would the smaller missions also track the uncertainty of their products, or does it only happen in the larger missions?
Well, it depends what you mean by track the uncertainties. um, they want to, but you get into an issue of trying to determine what the truth is. So I want to emphasize that some of the biggest problems are due to lack of calibration accuracy. And that's a real problem for small systems because small systems, many of them don't include black bodies on board. So it's very difficult to measure the absolute radiance that you're seeing. Uh, it's also difficult to track the drift in the detector response. Uh, and then there's the self emissions. And that, of course, changes as the temperature of the telescope changes. And it can change different elements at different points in time. All of that becomes an issue. So you have to do frequent calibrations, good accuracy, in order to correct for all of these issues that occur. Small systems tend to like to take shortcuts. And as a result, they can't meet the accuracy that a large mission could with onboard black bodies, lots of thermistors, and so on.
So we're back to the constraint of costs.
Yes, everything always comes down to cost, unfortunately.
So we have seen already quite some insights into the differences, but what about the synergies? Can the commercial data be used together with the agency large missions? And what are the restraints? What are the conditions? What do the users, the remote sensing people, need to know about fusing those data types?
Well, the data can often be used together. Um, for example, the high accuracy of a large system can be used to cross calibrate to improve the accuracy of small systems. That can be a big help. Although, when you calibrate a system, you are assuming that your calibrator is truth. But if you're cross calibrating against a large mission, you're assuming that's truth, but they inherently have their own errors. So, having said that, though, it's still an excellent way to find some synergy between the large system and the small system. Once you've calibrated the small system against the large system, the small system can fill in the blanks at times between the collections of the large systems. They can be fillers, basically, because large systems typically do not have a very rapid revisit time of the same point on the ground, whereas the small systems tend to be part of fairly large constellations and they see the same point on the ground much more often. So they can help you get a better resolution in time of what you're looking at and relate that data to the small systems. Also, data from the large system can help with supplying information such as emissivity of the ground and atmosphere for the small system.
In the same wavelengths, oftentimes, right?
Typically, I would say yes, but at the moment, the company that I'm working with is using a slightly different approach where we look at, instead of comparing the same wavelengths, because you always have problems if the large system has a certain wavelength bandpass and it's different. Typically, what you have to do is you have to come up with some kind of a spectral response function correction factor between them. However, if instead of doing that, you compare temperature between the two, you calibrate in the temperature domain rather than in the wavelength domain, you don't have to worry about creating spectral response correction factors, which is more accurate.
We have now both kinds of sensors, large agency missions and small commercial missions. And now we know, for instance, that the companies like Constellar or Aurora Tech will be taking part in the Copernicus contribution missions. So basically, any user can download the data equally from future sensors like LSTM or SPG and then take it together with data from those two companies. And now, can the users just ignore the fact that they will come from different sensors, or should that be consumed with some caution?
Well, you're getting back to the issue that I mentioned about calibration and how good each system is. Um, I think that you'd have to take into consideration the source of whatever information you're looking for. Because again, the small systems are not calibrating as carefully or as often as the large system. Also, it's very difficult to validate the information once you're on orbit. Um, Now, some systems will try against certain ground targets, but those are single points, and you may not know exactly what the performance is for any particular image at any particular time. So I think what you would have to do is hopefully assign some kind of a confidence level to the readings of each system so that if, let's say, LSTM was supposed to have an accuracy of 1 degree, um, maybe one of the small systems might have an accuracy of 2 degrees, but you may not know that. That's part of the problem. Validation is always an issue, and it's especially difficult for systems in low Earth orbit, as basically all of these systems are, because it's almost impossible for both a small system and a large system to see the same point on the same at the same time on the ground, which means you don't know what's happening between the collections and what's changing over time. Does that help?
Yeah, so users be advised on looking into uncertainties. Are they reported or not?
Yes. Yeah. You always have to be careful about the source of your information.
And that's the end of the first segment with Ellis Freedman about how large space agency missions are different from smaller new space missions of recent times. Stay tuned for the second segment, where we'll be talking more about thermal mission design in the next episode of Thermal Lens.